All right, let's get going. Okay, so last week you got all of the fundamentals, basics, everything you need to know. I'll throw in a few things along the way that we didn't cover, but they'll show up when I show you some diagrams. So now we're going to look at some diagrams and see what they tell us. So this one I've drawn, rather not so nicely, but it's good enough, is the system magnesia, silica. This is an important system in ceramics because it's present in a lot of steel-making applications and refractories. Okay, so this diagram should tell us something relevant to high-temperature behavior of these things. So the first thing we want to look at is the units of this diagram. So the ordinate is in what units? Ordinate, the y-axis, for those of you who don't know the meaning of the word ordinate. The y-axis is in what units? Degrees centigrade. It's there for you. What are the units of the abscissa, the x-axis? What are they? Yeah, they're percentage. What kind of percentage? Weight or mole? Or volume? Which one? How do you know? Because MS is not at 50 and M2S is not at 33. Right? So they're not stoichiometric. It must be a weight percent or volume percent if you're a dodo head. Right? So there are how many intermediate phases in this system? 2. How many congruently melting compounds are there in this system? 3. What are they? M2S, NGO, and silica. How do you know NGO and silica? How do you know NGO is congruent melting? It's not even on the phase diagram. Cuts off. How do you know? All Lindon members have to be congruently melting, or it's not a true binary. So what's the congruent melting point of silica? 1723. What's the congruent melting point of M2S? Right. M2S is 2 magnesia, 1 silica, and the mineral name of that is forsterite. MS is 1-to-1, and that's called enstatite. Okay? You're not responsible for mineral names, but these are very well-known phases, and when you work in the field long enough, you come to know most of the mineral names. 1890, is that a high melting point? Would you consider 1890 to be a high temperature? Yeah, it's very high. So right here, we're looking at a refractory material. Silica, 1723. Okay, but the fact is that generally, silica forms a glass. So we rarely actually melt silica. We generally form a glass at quite a bit of a lower temperature than 1723. Right? But glass is a metastable phase. And so it shouldn't be on the phase diagram. But it's a reality. Now, so how many incongruent melting phases are in this system? Raise your hand if it's 1. Raise your hand if it's 2. Raise your hand if you don't know. Oh dear. We covered this so many times already. Those of you who raised your hand, you clearly didn't look at your notes, and you were behind. Congruently melting. has a melting point and it has a dome on top. It goes from a solid to a liquid of the same composition. If it is incongruently melting, there's no dome. It goes up and it cuts across. That's a paratectic decomposition. It has no true melting point, but we call it incongruent melting. Everyone should have known that. This is fundamental. I am now concerned about your level of understanding because this is totally basic. And for so many people to raise their hands at this stage tells me the message is not getting through. Why not? You didn't look at your notes, and you've forgotten it all. And I can't be in the habit of repeating everything ad nauseum because you guys haven't pulled your socks up and worked. You want to pass the exam, you have to do that. You cannot sit on your lazy asses and do nothing because this class is not about memorization. It is about understanding how to use these diagrams. So if you couldn't tell me these fundamental things, you need to get busy and start looking at these things so you remember something. Because I'm not going to review all of the basics again. Not a chance. I've got 2 weeks to cover this. And I got 1 week to tell you how to use these diagrams. Those of you who are not familiar with these fundamentals, shame on you. You should do better than this. I'm very disappointed. 1 incongruently melting compound. 3 congruently melting compounds. What's that dome-shaped thing on the right? What is that? What's it called? The dome, not the invariant point. What's it called? What kind of gap? Miscibility gap. What's inside the miscibility gap? 2 liquids. What's up here? Liquid. What's in here? Right up here above 1850. MgO plus liquid. How do you know? MgO's on the left, liquid's on the right. What's in the big rectangle? What's in the small rectangle right next to it? How do you know? Because what's on the 2 sides of it? What's in the rectangle next to that? What's in the small thing right here? MS plus liquid. What's in the big thing right above it? How do you know? What's on the sides? What about this small wedge on the other side of the line? Same thing. I just swapped the order around. What's in this little triangle on the right-hand side? Right on the edge of the diagram there. What's in there? How do you know? How do you know? Liquid's on the left. Silica's on the right. What's in the wedge right here? What is it? What's in that wedge? The big thing. Right here. What is it? Liquid plus. Have we seen L plus S before? We have. So why do we have the same thing twice? Because the liquids are different compositions. Same thing with around the Forsterite. One on the left and one on the right. Just 2 different liquids. All right. I have completed the phase diagram. I've labeled it. Now, first conclusion we can make from this diagram is that if I put magnesia in contact with silica, what's going to happen? They're going to react. That means they are not what? Compatible. What will they react to form? No, that doesn't depend on the temperature. We are at equilibrium. Temperature is irrelevant unless I go up and change into a liquid or something. Okay, I'm asking what solid phases will be the reaction products. What will they be? M2S and MS. How do you know? They lie in between the two end members. There's a phase between the two. That means they don't like each other. They react to form that phase. We have two possibilities. What are the possible phase assemblages if I react magnesia with silica? What are they? How many are there? How many possible phase assemblages? You should know this very quickly. How many? 1? Raise your hand. 2? 3? 4? 5? 6? Who doesn't know? Raise your hand. I'm only going to gently abuse you. You raise your hand. Raise your hand. I need to know if you don't understand. All right, fair number of hands. The number of phase assemblages is how many mixtures or single phases can be present as reaction products. If I have a composition on this line, that's 1. If I have a composition on this line, that's 2. If I have a composition in this field, it's 3, 4, 5. Okay? We don't consider the end members because there's no reaction. They are the starting materials. There are 5 possible phase assemblages. 2 have 1 phase. 3 have 2 phases. Okay? Everyone should have known that. All right? We have been through this also multiple times. What is the paratectic decomposition temperature of enstatite? The paratectic decomposition temperature of enstatite. What is it? Just say it. 1557. Okay, well, it's written there for you. What are the reaction products when we decompose enstatite? M2S plus liquid. How do you know? You know because the phase diagram tells you. When you heat M2S, it reacts to form that, and that is your lever. Question 2. How much liquid and how much solid are present when you decompose enstatite? How much? Which one's the major phase? Forcitrite or liquid? Which one? Somebody says liquid. Why? The line is closer to the liquid line. That's a vague answer. Give me a very specific answer. Which line are you talking about? This line is closer to this point. Okay, be careful. Make sure you give your answers very precisely. Because if you give me some vague answer and I don't like it, I won't give you credit for it because you haven't convinced me you know what you're talking about. The point at which enstatite decomposes is very close to the liquid. It's about 80% liquid and 20% solid. But if you use the inverse lever rule, you can calculate exactly how much, and you will be required to do this on the exam. Okay, so it's about 80% liquid, 20% solid. Well, that's a pretty big shift, isn't it? So if I've got enstatite, even if I've got a few grains of enstatite, and I heat those up, what are they going to do? I'm going to have a whole bunch of droplets of liquid throughout my microstructure. That could cause shape distortion. It could cause solubility, but of course, is there any solubility in this system? How do you know? The answer was no. How do you know? How do you know there's no solubility in the system? It's all straight lines, or there are no solubility homogeneity regions. Okay, so no, the liquid's not going to dissolve. Oh, wait a minute. That's solid solution we're talking about. Solid solution. But I've just been talking about liquid solution. Do not the liquids all dissolve solids? Aren't every one of those liquidus curves a solubility limit? Oh, crappo. I screwed it up. You got led down a path because we're talking about liquid solutions, not solid solutions. And I didn't tell you what kind of solution I was talking about. So now the question is, can this liquid dissolve anything? Let's ask ourselves if the diagram tells us this. I've decomposed this thing. I've heated to 1560. So I'm right here on the phase diagram. And I have a liquid and forsterite dissolved in it, isn't it? And I've got a solubility limit. And if my starting composition was here, and the liquid shifted over to here, then here's my composition right here at 1600, and I draw a lever across here, and I calculate this liquid, this solid, that much, and I can actually tell you how much is dissolved, how much forsterite is dissolved, or how much magnesia or silica, whatever is dissolved, because here's the solubility limit of forsterite in the liquid. And that's a solubility limit. So here's my composition. I can say there's this much magnesia and this much silica in it. I can give a composition of the liquid, which is the way I have to do it. And there's a solubility curve. And that says if it's over here, it's unsaturated. And if it's over here, it's saturated. But my composition's here, so I obviously have a saturated liquid. And the liquid is saturated in forsterite. It's saturated in forsterite. Now, I have a very refractory material in forsterite. Okay? But it's made from naturally occurring raw materials, which means there's crap floating around. And my composition is not necessarily on forsterite. So it's quite common that I might have a little bit of quartz grains contaminating my magnesia, and when I heat it up, those quartz grains react to form enstatite. Because if I put magnesia in contact with silica, the two compositions are moving this way. And I want them to move right onto forsterite, but that extra quartz screws me up, and it shoves my composition over here. So now I've got some impurities of enstatite. I have to deal with those. So those little grains of enstatite, which are contaminating the forsterite, when I heat this up to 1600, which is not an uncommon temperature in steel making, those guys are going to decompose, and they're going to form this liquid, and that liquid's going to dissolve some of the forsterite, which means I'm going to have a microstructure that has a grain of enstatite in it, and it's going to form a liquid, and it's going to dissolve some of the surrounding forsterite into it. And then it's going to solidify. I'm going to have this region that's completely altered because it started as enstatite, and that has a specific volume, and it's going to be different from that of forsterite, which means it'll either contract or expand. Now, if it contracts upon solidification, it pulls the bulk into compression, and with a brittle material, that's okay. But if it expands and it's a brittle material, that's not okay. That's very bad. So I've just weakened my material really badly simply because I have some impurities of enstatite. And these are the kind of things I expect you to be able to figure out in an exam. Now, of course, if I'm relying on a mechanical issue, I have to tell you these considerations. But it doesn't really matter whether it expands or contracts. One's okay, one's not okay. The point is, you have an impurity, it's going to decompose, it's going to form a lot of liquid, and that liquid will dissolve your matrix, which means it goes even bigger in its effect. And wherever it's liquefied, if If I have a porous refractory around it, it solidifies there, and I filled up my pores, and I've got a big, huge chunk which is not compliant. If I have really tiny particles, they can take a lot of stress, and the matrix can hold up under that stress. But if I've got big particles, no. It concentrates it because it's a big, stiff particle. And the matrix has a lot of trouble handling that kind of stress. So I can read this from the phase diagram that I'm going to have some trouble if I can't control my composition really well. So if I shove in some excess silica, then I run the risk of forming enstatite, and that guy decomposes at 1557. That's bad. But it's even worse. Because if I've got excess silica, and my composition is not here, but is over here, now I'm really in trouble. Because the liquid finite form is 1543. That's lower than 1557. It's not a big, huge temperature drop, but it is a drop. And once you form a liquid, you've got big problems, because all sorts of things happen with liquids. They're high diffusivity paths, reactions are sped up, a porous material gets saturated with liquid, and then when it solidifies, it shrinks like crazy, and you got stress problems. Ceramics, we don't melt. They're brittle, they don't like it. Not only that, here's where your liquid is. So, lots of silica, less silica. So the closer I am to this composition, the worse it is, because that becomes 100% liquid. That would mean complete melt, well, not melting, but complete liquefaction of the whole body if I have this much silica. So what I really want is a tiny bit of silica over here. The problem is the compositions are moving this way during the reaction, so they have to cross these phase fields. And if they cross and they form a liquid, or they form a liquid, that liquid's there. It's a transient phase, but it screwed up your microstructure. So you got to be cognizant of these things. So here composition is really important, because you could go from 1890, which is very refractory, or if you manage to get equilibration without having to get screwed up there, look at your invariant point, 1850. That's very refractory. So here's another good message. If you have a composition that's magnesia rich relative to forsterite, it's refractory. But if you have a composition that's silica rich, that's your relevant invariant point. You're in trouble. It's not refractory. So this diagram you can divide into two regions. Refractory, not refractory. So remember, the melting point, not very important. What's important is the invariant points, those eutectics. How many eutectics are there? Three eutectics. Raise your hand if you see three eutectics. Raise your hand if you see one eutectic. Raise your hand if you see two eutectics. Are you the only one with your hand up? You got one? Raise your hand up if you see two eutectics. Hi. You guys are right. Everyone else who said three is wrong. Why? The one on the right is a monotectic, not a eutectic. There's two liquids there. Right? That costs you a point on the exam. Every mistake is a point off. I don't give points for correct answers. I take points off for incorrect answers. How many melting points are there? We've already covered it. Congruent melting is a melting point, so there's three. All right, so we have invariant points. Two melting points, a monotectic, and two eutectics. Right, those are five invariant points. Now I want you to look at this liquid at surface. It's very steep, isn't it? It rises up very quickly. Same thing over here. It rises up very quickly. Let's take the two extremes. Let's say there's one liquid surface that's steep and one that's very shallow. Okay? The one on the left is what I'm looking at here. Okay? Now I want you to visualize two compositions. One is here and one is here. And now I want you to visualize the heating of these things along an isopleth. And now I want you to visualize the levers that are formed as we heat. So here's a whole bunch of levers here over a wide range of temperatures, and here's a bunch of levers over a very narrow range of temperatures. Okay? What have I just plotted and shown you? Anybody know? What can you conclude from what I just did? Anybody got it? Sorry? Which one's a more powerful flux? Well, yeah, okay, that's one conclusion you can get, not from the levers though, but she says one's a more powerful flux. So which one's the powerful flux? The one with the steep liquidous surface or the one with the shallow liquidous surface? Shallow? Really? B is a more powerful flux to A. Well, I better put A and B here, huh? So you're saying that which one's the powerful flux, A or B? B is the strong flux, correct? All right, what's the definition of a flux? What's the definition of refractoriness? A flux lowers the refractoriness, right? How does it do that in terms of how we define what refractory is? Who does not remember what a refractory is? Hand up. Give it a go.
Refractoriness is the resistance to phase change.
No. It's resistance to what? Wrong word. Not melting. That's a melting point. Liquefaction. Okay. So it's a resistance to the formation of a liquid in terms of what? Two parameters. Two parameters I gave you for refractoriness. If you looked at Moodle, you'd know this. You remember? It's what temperature the liquid forms at and how much liquid you have. Okay? Now I've got somebody here saying one is a more powerful flux, but that depends on how you're going to define the flux. If you define the flux in terms of when the liquid forms, which one's the more powerful? A or B? The temperature at which the liquid forms. Which one is the more powerful flux? What did you say? She says B. What do you say? Which one drops the liquidus temperature the most? B is the more powerful flux, obviously. It goes from high to low, so it's got a steep liquidus curve. That's a powerful flux. So B fluxes A very readily in terms of the drop in temperature. But what if my criterion is the amount of liquid? Which one forms a liquid more rapidly? In other words, which one has the more rapid rate of liquid formation? It's real obvious because I just did it for you. Which one forms more liquid more quickly? Is it on the left-hand side of the diagram or the right-hand side of the diagram? The right hand, because the levers are changing their proportions very rapidly over a narrow temperature range. That's a fast rate of liquid formation. Whereas the one on the left, you see the levers are almost constant. So in other words, on the left, the amount of liquid solid, well, the liquid-solid ratio is hardly changing until until you get to the very highest temperatures. So that means it's the other way around. In terms of the amount of liquid formation, B doesn't do much fluxing of A, does it? Okay? So it depends on how you define it. Normally, we look at the temperature. That's your first point, and that's your general way you would assess this. Okay? But you see, it's a little more refined than that, isn't it? So this one is constant rate of liquid formation, and this one is changing rate of liquid formation, rapidly changing. So that tells you, be careful, because if you have a shallow liquid surface, got big changing levers, which means the amount of liquid is hard to control over a narrow temperature range. And a lot of furnaces have big temperature gradients, and they fluctuate. You got a problem. But if you're over here on the A, you'd say, well, I have a lot to play with here in terms of liquid-solid ratio. It's pretty constant over a big temperature range. So as long as my composition is about right, I can nail it, and I can process this with confidence. Okay? And when we have ternary phase equilibrium, I'm going to show you a system, which is why it could be made hundreds of years ago with crappy furnaces and crappy raw materials, specifically because of this effect. That's porcelain. So this is about rate of liquid formation, but it's also about extent of fluxing, and that's refractoriness. So when you see these steep liquid surfaces, this tells you that that's good. It's a very powerful flux. That's bad. But in terms of amount of liquid-solid ratio, that's good. The other thing that's important about liquids, which we don't show on the phase diagram, is indicated by that Greek letter, and that's used for viscosity. And the problem that we face with any liquids, including glasses, is that the log of the viscosity versus the temperature goes like that. And that tells you that the viscosity changes very rapidly with small changes in temperature. Now, I knew this from my reading of many, many years, but I was doing a consulting case, and I thought, I'm going to put that to the test. So I replotted in a linear plot. It's incredible. The viscosity really does change enormously. 10 degrees can double the viscosity or have it. So there's big changes, and that viscosity is really important because when it's thick, the particles tend to hold together and you can maybe retain your shape. But when it starts to become runny and thin, it all just slumps out and you lose your shape. And that means it happens over a very narrow temperature range for glasses. And for other liquids, it's even worse. All right, so that's a basic principle. You're not really responsible for that in this class, though. But that's a consideration when we're talking about liquids. Now, the question about that, can I go back? Yikes. There we are. The question here is, how much liquid can I have? What will its viscosity be? What can I tolerate before it slumps? We don't know. And on top of that, we've got another problem. This is a weight percent diagram. So if I tell you I got this much liquid and this much solid, I have this much weight percent liquid and this much weight percent solid. But I need to know more about the liquid. Because if I'm going to estimate its molecular weight, or I'm going to know its molecular weight, then I need to know the composition. And the composition of a liquid to get the molecular weight is not easy because it's not additive. You can't just add up so much of this, this, this in proportions and say, that's it. It doesn't work that way with liquids or solid solutions. So there's no simple way to get at what this really means when you say this much weight percent liquid and this much weight percent solid or mole percents. Because what you really need to know is volume percent. And to get the volume, you need to know the density. But you don't know the density of the liquid. Fortunately, most glasses have similar densities, and most of these systems, being silicates, form glasses. So we can guess and assume it's going to be close to most glasses. It's good enough. But that's a problem, because really it's about volume percent, not weight percent, because it changes depends on what the relative densities are. Okay, so be careful. It's kind of a black art here when you're talking about liquid and solid. So just bear in mind, you need to know if your diagram's in weight or mole percent, and when we're talking about microstructures, it's volume percent that counts, not weight or mole percent. It's a little tricky and dangerous stuff. What happens if I take this composition up to 1700? Well, it will liquefy, and I will have a miscibility gap. So in your mind, you should have a picture of oil and vinegar. These two liquids don't like each other, but who cares? It's a liquid. It's completely slumped. But wait a minute. Maybe I want to cast these things. Maybe I do want to melt this thing, pour it into mold, and hope it holds together. So if I take this whole system and I ask you on the exam, if you're going to cast a shape from this system, and that means I haven't given you a composition. If you're going to cast a system, you need to know what cast means. That means liquefaction, poured into a mold. If you're going to cast from this system, what composition will you choose to have the least expensive process? What composition are you going to choose? Least expensive process. Where is it? Raise your hand if you know how to answer this question. Okay, raise your hand if you don't know how to answer this question. Okay. Is the problem you don't know what determines the expense of a system? Yes or no? All right, well, the main cost to processing is energy. All right? So in terms of energy inputs, what will be the least expensive composition to cast from? Where is it? What temperature and what composition? 1543 at the eutectic, because that's the lowest temperature at which I can completely liquefy my system. So this is a really simple question to answer. It's a giveaway. Okay? What would be the most expensive to cast, excluding the end members? Forsterite, because that's got to go to 1890 to melt it. And it melts, okay? To melt it. All right, so if I want to cast forsterite, can I do that? Will it work? What if I want to cast enstatite? Will that work? Who says yes? Raise your hand. Can I cast enstatite? Who says no, I cannot cast enstatite? Why not? It's incongruently melting, which means I cannot get a homogeneous liquid of that composition. In fact, my next question is, if I am a little bit dopey and I want to cast enstatite, what temperature do I have to take it to liquefy the composition? What temperature do I have to take it to liquefy the composition? How do I do it? Raise your hand if you know how to answer this question. Okay, raise your hand if you don't know how to answer this question. Okay. If I want to liquefy the whole system at the enstatite composition, I have to take it so it crosses the liquidus surface. So I just extrapolate, and then I read the diagram. Over here, it's about 1700. Easy. You just have to know how to do it. Okay? Now, the next question. What will my microstructure look like? So if I heat this, you get complete liquefaction to here, and then I cool it down by pouring it into a mold. What's the first thing that's going to happen? What will happen? What precipitates? How do you know? Because the phase diagram tells you what's going to precipitate. Forsterite. So your primary phase, the first to precipitate, is forsterite because the composition enters M2S plus L. So the liquid composition is going to move along the liquid surface as you precipitate forsterite out of it. You cool it down all the while. That's a big temperature drop, 1700 to 1557, so 150 degrees of the kinetics. You're going to be precipitating your primary phase, forsterite. So the grains start to precipitate, and as that 150 degrees takes a long time to cool down, every time you precipitate a forsterite molecule, it's going to precipitate on some pre-existing molecules, and the grains are going to get big and bigger and bigger. Real bad for your mechanical properties. 150 degrees of this crap to put up with. Crap microstructure now. So you've precipitated forsterite for 150 degrees until you hit 1557. Then what happens if you are at equilibrium? What will happen? If this is an equilibrium process, what will happen? Two things will happen. What are they? Or you can pitch it in one thing. What is it? That's correct. At equilibrium, they should react. What is they? What does they consist of? Forsterite liquid. How do you know? They're on the line. On the ends of the line. Okay, so your primary phase of forsterite that's precipitated out is going to react with the liquid in the paratectic reaction and go on to enstatite. Is that really going to happen? No. Long. So now that's the next part of the question is at equilibrium, what will happen? Second part is under real world conditions, what will happen? What are you going to end up with in the microstructure in real world? In the ideal, you just got enstatite, but in the real world, what's your microstructure going to look like? You got to be careful about your answer here. You got to think real hard about what's actually happening. Okay? You precipitated primary phase. Is that all going to disappear? No. So definitely you're going to have some residual forsterite. But when you hit the paratectic, it's forsterite plus liquid forms enstatite, right? So the remaining liquid will react with your primary phase. Where will that reaction take place? Between the liquid and the forsterite? Where will it take place? On the surface of the forsterite grains, at their grain boundaries. So that tells you you're going to have some primary phase sitting in the middle of a reaction zone that's got liquid plus forsterite. So the liquid basically attacks the surface of the forsterite to form enstatite. And so you're going to have a microstructural disturbance, and that's coring. Okay? So it's going to have a primary phase of forsterite surrounded by an ugly-looking little region where a reaction took place. So it's kind of a disturbed region. And then outside of that, you should have pure enstatite. May not get that. It may actually shift over here, but that's a different issue. I won't go into that. Okay, so that's what your microstructure would look like. So there's two answers. There's the equilibrium answer, and then there's the real world answer. And you need to be aware of these. Even though this class is about phase equilibria, it would be irresponsible of all of you not to understand that we're not always at equilibrium. And so we need to be aware of these things too. Okay? So I can cast this guy because it's congruently melting. I cannot easily cast this guy. Of course I can cast it, but it's not going to work very well. Enstatite, not very desirable. If I cannot cast enstatite, but what I want is enstatite for some stupid reason, what will I do? I want a dense enstatite. What does the diagram tell me I have as an option to do? What is it? Somebody give it a go. What does the diagram tell me I can do to make dense enstatite? What do I do? What? You're laughing. You're not certain of your answer? Oh, that's okay. It doesn't matter if you're not certain. What I need to know is if you know or you don't. Who doesn't know the answer? So you all know the answer. Now, raise your hand. Show me. Brag about your ignorance. Raise your hands if you don't know. Okay, I need to know this. What are my options to make a material? I can cast it. What are the other two options? Solid state densification or liquid phase densification. Can I solid state densify enstatite? Yes or no? Raise your hand if you don't know the answer to this. Okay, you guys are behind. You can solid state densify anything as long as you don't form a liquid. Of course you can. You can go from here to here, solid state densification. We have done this in the class. You're behind. So that's a dopey trap question. It's a giveaway. And if you don't answer it, I know you don't understand. And that's a big deal, because when I look at an exam, I can tell if you understand or you don't. What about liquid phase densification? What do I need as a prerequisite for liquid phase densification? Yeah, you know, liquid, that's true. But there's a little more detail than just having a liquid. What do I need from the phase diagram? Raise your hand if you know the answer to this question. If you know the answer, raise your hand. Okay, you, right there. What's the answer? Can you be more specific?
So if you want enstatite, there needs to be a phase.
That's right. You need a solid plus a liquid. They need to be compatible. You can't have a liquid phase densification aid that reacts with your material. So you need liquid plus that material region. Do I have one?
Yes.
I do. It's right there. I labeled it for you. Right there. It's kind of small, isn't it? Which means I have only 14 degrees in temperature variation, and I have only about 7 or 6 weight percent to play with, which means I'm screwed. Because my temperature fluctuations are going to be big, and my compositional variations are going to be big. And if I'm trying to make enstatite by liquid phase densification, I need to have really good process control and really good raw materials control. Very unlikely. That's a loser. Not good at all. What if I want to densify forsterite? You'd be stupid to cast it, because first of all, casting the ceramic is dumb. It's always going to crack. So you're going to densify it. And when it's very refractory, what did I tell you you needed to do to get solid state densification? What was the temperature range? Nobody remembers? It's around 3/4 of the melting point. 90% to 75%. That's going to take a lot of energy. Can I do this at a lower temperature and get an even better result? Because solid state diffusion is slow, and liquid phase is a fast diffusion path. So, do I have another option with forsterite? Can I liquid phase densify forsterite? Do I have a big temperature zone and a big composition zone to play with? Is the liquid-solid ratio constant? Oh, beautiful. So there's a winner. There's a loser. Sorry?
Why would you have trouble liquid phase densifying forsterite when you've got an
MS is irrelevant. Are you saying if we cool it down, we're going to get that? Ah, well, that's the next thing. I can liquid phase densify forsterite, correct? By taking, say, this composition and heating it at 1600, and then I've got easy control of how much liquid, so if I experiment, I find out what I need. So the temperature and composition I determine experimentally. And then we had a relevant question. What happens when you cool it down to room temperature? Well, that means you're going to go down here. And what will your phase assemblage consist of? You'll have a little bit of instantite, won't you? This is the price you pay for liquid phase densification because you have to go off composition. You got to go off. So we're down here. Okay, so that's my mixture. So the next question is, having liquid phase densified forsterite, if you're going to market this product, what are you going to tell your client is the maximal temperature of usage? Maximal temperature of application. What is it? Raise your hand if you don't know the answer to this question. All right. If you heat it to here, does anything change? Does anything change? Does anything change? Does anything change?
Yes.
A big liquid change. I got liquid. I got no liquid here, do I? So my microstructure, all I've got is maybe a bit of grain growth, some crap like that, but you know, that's just the way the world is. But nothing's changed. But if I go above 1557, I got a big change. My instantite's disappeared, and I got a lot of liquid. And remember, this can be quite different from here. Now these happen to be close, so this says I've got, 5% instantite. And if I go over here, I might have 1% liquid, which might not be too bad. But over here, it's actually a much higher level of liquid. So the width of that thing and the lever that's formed also tells me if I'm going to have a lot of liquid or a little liquid. Sometimes a little liquid you can survive, but not a lot of liquid. So you got to be careful. And the diagram tells you that if you know how to read it. So 1557 is my maximal temperature of usage. And then, of course, you build in the safety factor and say, look, guys, don't take it above 1500. We do not guarantee the product if you do. And then you sell this product, somebody puts it in the furnace, and it fails. And they say, we're going to sue you. And you go, okay. And then in the court, you have a discovery process where you demand samples. So you get the samples. They send them to me and pay me for this. And I examine them. And I'm going to look at the microstructure. I'm going to x-ray it. I'm going to look at the microstructure. And I'm going to be looking very carefully if there was a liquid that formed. Because if the liquid did form and it was relatively pure, these two phases, then I will know for sure that they took it above 1557, and it's not the company's fault. It's the user's fault. They drove the furnace too hard, or they overheated, whatever. I see this lots of times. Just, they don't know how to treat the furnace. Drive it too hard, and the stuff deteriorates. A very big case on that, just that very thing in Melbourne, a number of years ago. Very big case. All right, so, good message there, small. Good message there, big. Good message there, don't go above it or you've changed your microstructure. Very bad. If I want to cast this guy and I go up into two liquids, it's quite possible that I will freeze in that microstructure. And that can be good or bad. Generally, you consider it bad because one phase is better than two. Because two phases do ugly things. Because they got different coefficients of thermal expansion. With one, it's more homogeneous. All right, better take a break. 5 minutes.
L. Right. Oh, that's S2, S3. So about it's on the liquid research. I'll take my word for it. This is on the that's the well, oh, that's all in that liquid tank. So you might as well, that's the starting point. I don't understand it anymore. What this says is the liquid is paratech reaction. This is a reaction of this force. Yes? Same with the detector. The detector, what happens is that the reaction point corresponds to the that's all right. Diagram. Yeah, okay, okay. Okay, thanks.
All right, let's get going. Right. This is another important out to 70% alumina, and that composition is MgO-Al2O3, which is abbreviated by Ma, and that is the prototype for spinel. There are many, many spinels structures. There's cubic structures. There are lots and lots of them, but this is the prototype. So this is the true spinel. Is this diagram in weight or mole percent? Yes, you can. Which one is it? Weight or mole percent? How do you know?
Because MgO and Al2O3 are exactly 1 mole each part.
That's right. Spinel's 50-50, but it's on 70. Must be weight percent. Right? Everyone should have picked that out. Is there a partial solubility in this system? Is there a lot of it? Are these extensive ranges of solubility? They are. Very frequently we might have a couple percent. But this solubility region goes to about 18. And that one goes, I don't know, it's about 10. So we'll make that 60. Okay. That's big. Where's the solvus line in this system? Where's the solvus line? Which one is it? Show me with your hands what it looks like. Who doesn't remember how to identify the solvus? Raise your hand. So all the rest of you do? Want me to pick on somebody? I don't believe it. Raise your hand if you don't remember where the solvus line. Which one's the solvus line? All right. This is the solvus. This is called the sol index. Except I got it backwards. That's the solvus there. Doesn't matter. The point is that we got two of them here. And they're, standard terminology, that's called a liquidus. Okay. Is there a eutectic here? Is there a eutectic? We would make this assumption that this is liquid here, especially as we probably have a melting point of 2800 and another melting point of 2105, but it actually could be eutectoid. But if that were the case, I'd need to show a big solubility lens there up top. Otherwise, it's not very nice of me. So yeah, there's a eutectic there. It's right here. Okay. Now, the solubilities, you'll notice, all decrease as we cool down. And normally that's what we think. Low solubility, low temperature. High solubility, high temperature. But you can see that when you go up, I had it right in the first place. Not to worry, you check your notes. When we go above the eutectic, it reverses. So we can't just say, as we drop in temperature, the solubility always drops. That's not true. Because the liquid solubility actually goes the other way. The solid solubility does go that way. Now the key issue about this system is the big solubility regions and the relative refractoriness of the phases. 2100 is a very high temperature. So if I take some magnesia and some silica and I put them in contact, they're going to react to form spinel. Now what I can do is plot spinel here. We know it's congruently melting. We know there's a big solubility region. So it's going to go like that. Oops, that's not very good. Okay, so that's the part we're looking at. That's wrong. That goes up to there. So there's silica. That's, alumina. Okay, so if that's alumina, that is 2020. This is magnesia. That's about 2800. I don't know what it actually looks like, but I dare say it looks something like this. I don't think there's any solubility. I'll get there yet. Okay, it probably looks something like that. And here is the spinel solid solution. But you'll also notice a big solid solution over here. And I've drawn it without a solid solution over here. So is magnesia soluble in alumina, or is alumina soluble in magnesia? Which one is it? Alumina is soluble in magnesia because we can see the homogeneity region of magnesia. So that's the matrix, comes out, and it's dissolving some alumina. What is the maximal solubility of, what is the maximal solubility of alumina in magnesia? What's the maximal solubility of alumina in magnesia? It's on the phase diagram. 18 what? Weight percent. Raise your hand if you know that, if you can see that. Raise your hand if you can't see that. Okay. It's obvious. That's the maximal solubility, that's the furthest projection, and I wrote 18 on there. That's quite high. So, I want to sinter magnesia. That is not easy. Magnesia's got a melting point of 2800. That tells you it's very refractory. What does it mean if something's very refractory? It means it's very stable. What does it mean if it's very stable? What it means is it doesn't like to diffuse. It's real happy being the way it is. So getting diffusion of the magnesium and the oxygen ions to cause densification is not easy to do. And all I have to do is look at the melting point or the paratectic decomposition temperature, and I can get a feel for whether I can have much luck in densifying it in the solid state through solid state diffusion, or if I'm going to need a bit of help with liquid. And I can look at magnesium and say, 2800, that's really high. Very stable, very unreactive, great refractory, but the problem is densifying it. But I told you, densification requires diffusion, and diffusion is enhanced by defects. If I form a solid solution, does that create a defect? Right, well, every one of those alumina ions dissolved in the lattice is a defect. And that helps things go along. Can I dissolve a lot of alumina in magnesia? I can. Lots of defects. And aluminium has got a 3+ charge, and magnesium's got 2+, which means I'm going to have an electron deficiency or surplus. So the magnesium is actually going to get an electron off of aluminium. That's a defect. So I'm going to have some oxygen vacancies in there. Well, that's good. So, exam question, does the diagram tell me if there are any advantages or little details that will help you solid state densify magnesia? And the answer is yes, it's a solid solution, so it's got defects. And, well, I wouldn't expect you to know about charge imbalance there, charge compensation, creating defects. I wouldn't expect you to know that, but I would expect you to know that that's a defect, and that will help you densify. So, yeah, there's a little trick that you can take advantage of. Go off composition. And then you'd say, okay, but remember, with liquid phase densification, going off composition came at a cost, because you had impurities. Is the same true here? If I take this much aluminium and I sinter it at about 2100, pretty damn high, and I get a really nice high density at 2100 and I cool it down, what's going to happen when I cool it down? What's happening there? What happens when I cross that solvus line? Phase change. 2 vague, 0 points. Forming, yes, you're going to have some solid solution of spinel, right? But watch out. It's not just going to be any old solid solution. Look what happens as the temperature goes down. Is the composition of the solid solution changing? All right, so the first precipitate was right here with lots of alumina. And as it cools down, the alumina is getting depleted. So that means my precipitates are all going to have a graded composition, aren't they? From high alumina in the middle to low alumina on the outside. If I can analyze that with a microprobe, or even a good SEM, I can tell what's going on. And then when I cross this line is just here arbitrarily to show you when the two solubilities reach 0. That's all that is doing. So basically it just stops. So this is not really a line here, but it's okay. We would normally have something to show there, rather than going down to room temperature 0. Okay, so I'm going to have a second phase precipitated, aren't I? Which is going to mess my microstructure up. All right? So the next question is, if I'm aware that I'm going to have a second phase precipitating, is it possible for me to minimize the microstructural disturbance through the processing, being cognizant that I'm going to have second phase precipitate? How can I minimize the effect of that second phase precipitate on the mechanical properties? What can I do? Anybody know the answer? Raise your hand. What can I do?
If you cool it rapidly,
Well, what will that do?
it will lock in the solid solution structure phase, and so it will just cool it down there.
The answer's right, but the explanation's wrong. Quenching is correct. That's the word you want. What will quenching do to minimize the mechanical stress on the system? What will it do? So if you reduce the time for the precipitate to not form, but to grow, will that give you small grains? And will those small grains cause less disruption to the microstructure than big grains? Now, so in fact, what I can do is use this to make a nanocomposite. So if I quench it pretty quickly, I might be able to keep those grains submicron size, and that improves it even more. In fact, that was the first time anybody did any nanomaterials with a ceramic person in Japan. He was the inventor of, well, not the inventor, but he was the first person to look at the mechanical properties of nanoprecipitates, and the properties were fantastic. Okay? So if I quench it, I can do it. The only problem is with ceramics, quenching them usually can cause thermal stresses, and you get thermal shock. So with a metal, absolutely, no problems. They will take the stress because they're ductile. And so quenching metals and the thermal history of metals is very important. That's why you have all these temper regimes in metals, to grow the precipitate to the right size or to keep them from growing too big. And then that's how you end up with the different grades of steels and all the different alloys of aluminium and what have you, is to control the precipitate and the grain sizes. In ceramics, we don't do that, but the principle's the same. Whether it's a ceramic or not, and you don't worry about thermal shock, the principle's the same. Rapidly cool, you can prevent grain growth by not giving it enough time. This is a non-equilibrium process. Okay, so the metallurgists have a harder life because they have another layer of complexity on control of the microstructure. And that makes their lives complicated from the perspective of explaining how to do it. But on the other hand, their lives are made much easier because they can control the microstructure. And this allows them huge flexibility in controlling the properties. The only ceramic that is used that requires a heat treatment is zirconia. And that's because one of the grains, if we retain it, we can get a process called transformation toughening. And we need to keep high temperature polymorph present when it's not supposed to be there at room temperature. And we can do that by keeping the particle size small enough so that the surface energy controls the process and it doesn't transform to the stable phase. That's the only ceramic that we do heat treatment of. All right, so we have a quite refractory system here with a eutectic at 1995. Fantastic. That says if I put spinel in contact with magnesia, I'm not going to form a liquid until 1995. And there are just hardly any processes where that's the case. Space shuttle, ooh, that goes really high. That's a problem, but that's about it. So we've got a very refractory system. We have a means of densifying either spinel or magnesia because of these solubility regions that will help us. Plus, look at the size of them. So that says even if we don't quite get the batching right, we're still going to end up with a homogeneous solid solution. And if we cool it relatively rapidly without thermally shocking it, we will have a small grain size of the second phase. We can do that. It's just, you've got to be really careful about how quickly you cool it. So we can see these two solubility regions here very clearly. Then, we say, very refractory from liquid formation point of view, and we're not going to risk that. So what we do have to worry about is these solid solutions. If I take a slab of spinel and I put magnesia on top of it, what's going to happen if I heat it to 1700? Okay? Alumina in direct contact with magnesia, what's going to happen? What are they going to do? Is alumina going to dissolve in the magnesia? Partially? Yes or no? Is the magnesia going to dissolve in the alumina? Partially. Do I have mutual solid solubility there? Do I have mutual solid solubility on this diagram? Yes or no? Raise your hand if the answer is yes. Raise it if it's no. Raise your hand if you don't know. Okay, not good, guys. Spinel versus magnesia. Are they mutually soluble? Raise your hand if the answer is yes. Okay. Did I phrase it wrong? Did I say magnesia? All right. I mean the two end members. Can you see that they're mutually soluble? They both have solubility homogeneity regions, right? So they're mutually soluble. So if I put them in contact, are they not both dissolving into each other? So what's going to happen at the interface? Sorry? What's the word? What's going to happen to the interface? They're going to stick together. Fuse means liquid formation. They're going to stick together because they formed a bond. They dissolved in one another. So there's going to be a zone of solubility because the ions diffused according to the temperature and the time you subjected them to. So you have the pure material, and then a diffusion zone, and they're going to stick together. Well, that's not going to be too good unless that's your goal. So there's another exam question. I want to bond these two ceramics together in the solid state without having to put a reactive metal in between to do it. Is it possible in this system? Yeah, it is. It's right there, staring you in the face. But then the question would be, if I want to use alumina as a spinel as a setter for magnesia in the furnace, is that a good idea? No, very bad idea, because my magnesia will be contaminated with alumina. My setter will be ruined because it's got magnesia dissolved in it, and it's going to stick to it. So when I pull it apart, I'll probably break my crucible. When I was doing my PhD thesis, I was heating silicon nitride and zirconium-based materials. And I was using alumina as setters. And I knew what was going to happen. I was going to get potential contamination from the alumina into the sample, or I was going to get my samples diffused into the alumina. Now, the alumina I used was from a furnace tube. We had broken furnace tubes, so I cut them up, and they were curved. And all my samples were disc-shaped, so they were contacting only on the edges. Well, that's good. Minimize the contact area, minimize the contamination because of diffusion. But what I did is I took those setters, and I just put them in a bed of my reaction powders, and I saturated the alumina with silicon and zirconium. And once it was saturated, well, you can't take any more. And so they turned kind of gray, but I never had any problems with changing the composition of my samples because I'd saturated them. Right, well, that's because I understand about this process. So I prevented a problem that a lot of people face just simply by subverting it up front. And this system would be a big problem because I know they like to saturate. But if I took this spinel setter and I saturated it first with magnesia, no sticking. So that would be the next exam question. Can you prevent this? Is there a mechanism to prevent this problem? And I wouldn't tell you what the problem was. So of course, if you can't figure out the problem, you blew it off, and then it's impossible to answer the next part. So that's a layered question, and you screw the first part up, you're done. You missed all the rest. Now, on the exams, if you make a mistake on the interpretation and there are follow-on parts, if you interpret it according to the mistake you made, I will not deduct points. That can be pretty expensive. You lose a point for getting the first part wrong, but if you interpret the follow-ons accordingly, that's okay. Right, so we see a number of things in this very, very simple diagram here. Mutual solubility, and both can contaminate one another. I can saturate them, stop the problem. I'm unlikely to get liquid under most normal situations, and both of the end members are very refractory. This is a very, very attractive system, and that's why it's a commercial refractory. Spinels are very well known as refractory products. A little expensive because they don't occur very commonly naturally, so they have to be synthesized, and that tends to be expensive because they're very unreactive, which means you need high temperatures to do all this stuff. Not so good. All right, so those were the two systems I had in mind to discuss today. So I'm just going to pick something else out here as an example. Too complex. All right. Okay, this is a cobalt oxide titania system. cobalt titanate. Titanates are very important in many systems, particularly piezoelectric systems. Who does not know what a piezoelectric is? Who does know what a piezoelectric is? Piezoelectric is a material that converts a mechanical signal to an electrical signal or vice versa. It's the principle all your speaker systems are based on. Any sound you hear that is transmitted from an instrument is done with a piezoelectric. How many intermediate phases are in this system? 3? Is this diagram in weight or mole percent? Weight or mole percent? Is this at 67? That is 67? Yes or no? Really? 190, 80? Is it 67? Is that at 50? Is that at 33? Is that at 33? No. None of them are on stoichiometric numbers, so it's weight percent. How many congruently melting phases are in this system? How many incongruently melting are there? 4 congruent, 1 incongruent. What is the incongruent melting point of the 1 incongruent melting phase? What temperature? 1505. Well, that's pretty high. All right. Is there any partial solubility in this system? Well, actually, we don't know for sure because maybe the investigators didn't determine it. So you've got to be careful about a lot of reported diagrams. Determining limits of solubility is a big pain. It's a lot of extra work, so often people just ignore it. But according to this diagram, no, there is no partial solubility. We have a melting point at 1575, and at 1470, we have a eutectic at 1410, and another one at 1430, and another one at 1520. Okay? So, what is the most refractory part of this system? What's the answer? Exam question. What is the most refractory part of this system? What's the answer? It's got 2 words with a hyphen in between it. Sorry?
The right side of the graph.
Right side. Really? Is that what you'd say?
The most liquid resistant.
If I asked you for the most refractive, what am I asking you? The most refractory. What am I asking you? If I don't give you composition, we can't be talking about amount of liquid, so I must be talking about liquid formation temperature. So which one's more refractory? What part of the diagram is the most refractory part? It's right there. I wrote it out for you. It's here, high cobalt oxide. The high cobalt oxide is because it's got the highest invariant point. That's the first liquid formation. Here, 1520. Here, the liquid onset is 1410. Here it is 1430. Here it is 1505. I can divide the diagram up into 1, 2, 3, 4 regions, and I can tell you when the liquid onset temperature occurs in each segment by looking at the relevant invariant point. Yep.
So why do we not consider the melting points?
Because I've told you repeatedly the melting points are irrelevant. It is the liquid onset temperature. I'm going to get lots of people on the final exam who are going to answer the questions in terms of the melting points. And what am I going to think? Dodo head. No melting points. Banish them from your minds. They have no relevance unless I specify a melting point. What matters in these systems is the invariant points shown in terms of the eutectics and the paratectics. That's what determines the refractoriness. It is not the melting point. If we're looking at a system globally, we're going to have the liquidous surface descending from two melting points. And if you looked at one was high and one was low, you could say, yeah, the melting points are high and low and they drop, but that's not really the issue. It's the liquidous surface. And it's irrelevant that the liquidous surface joins two melting points. What matters is where that liquidous surface is, because it may drop from one to the other, but it may also drop into the middle of the diagram like it does here. And so when we talk about the refractoriness of the system, the melting points have nothing to do with anything. What does matter is there's a minimum right here. That's the least refractory part of the diagram. Banish melting points from your heads. But I know bloody well that I'm going to get a bunch of exams with dodo head answers. Melting point, melting point. Get rid of it. 4 segments and we can figure out the refractoriness of each segment. This is the least refractory. This is slightly less refractory. And then I have 2 that are much more refractory. This one's 15 degrees higher. Therefore, the answer is unambiguous. It's the high cobalt oxide segment of the diagram that is the most refractory. I want to liquid phase densify these 3 phases. Contrast the relative ease or difficulty of each one. This is an exam question. The liquid phase, the intermediate phases in the system. So I've forced you to know what an intermediate phase is. Contrast the relative ease or difficulty. What am I asking? Because this is where my exam questions are. I don't say, where's the eutectic? I'll never ask that question. It will always be a practical question. Okay, so what am I asking?
So the temperature range and the...
That's correct.
The composition.
I'm asking what kind of flexibility you have for processing. So if the regions are small in one direction or both, you're going to have problems landing in them. But if they're big, you won't. So we assess it. And you can refine your question or your answers quite nicely because this region and that one up there are both C2T plus liquid. Over there, well, you need more temperature, but you don't have much to play with. So you need a higher temperature, but of course you have a more refractory product. And those are the multiple levels of the question I can ask. So if you want refractoriness, you got to go to the left, but you have processing problems. If you go over here, it's much easier to process, but look at how much refractoriness you lost. 1520 to 1410, so it's 110 degrees gone. So you pay the price. Well, on the left-hand side, you have better performance, but less guarantee of product consistency. And over here, you have less performance, but better prognosis to guarantee your product. So what do? You sell your product from over here because you say, oh, I don't want to perform as well, but at least I can make it. I'm not going to get a lawsuit. Because one lawsuit can destroy everything you've ever done. That's all it takes, just one, and you're gone. So you offer this. What about CT? Is that going to be easy or hard? It's going to be hard no matter whether you are cobalt oxide rich or titanium rich. You're screwed. You got 60 degrees here, but only too narrow here. This is only 40 degrees and narrow as well. Terrible. And it's not very refractory anyway. These are low temperatures and low melting, so the whole thing can liquefy at a relatively low temperature. And these are quite narrow, which means no matter what you do, you're probably going to have a lot of liquid. And that's another performance issue. Here you got a bit more to play with in terms of solid-liquid ratio, but here you don't. All these things are you can pick out of the diagram if you know how to read it and how to interpret it. If I want to synthesize or sinter this one, is it going to be easy or hard? Easy or hard? C2T, relatively easy or difficult? Liquid phase densify. that a big region or a small region? Big or small? Big. What's the minimal temperature for liquid phase densification I need for CT2? What's the maximal temperature I can use to liquid phase densify CT2? 1505. Do I have the same flexibility of going cobalt oxide rich or titanium rich to do liquid phase densification of CT2? Yes or no? I do not. I have only one side. I got no liquid over here, do I? That's solid state densification. And of course, if I'm going to do solid state, well, I'm not going to do a mixture of phases. That's stupid. I'm going to go right on to composition. But for liquid phase, I have to go off. Okay? So this guy's a winner. This guy's half a winner. This guy's no winner at all. So can I rank them? I can. These two are pretty good because they're big. That's got the bigger temperature range. That's got the bigger composition range. Which one's more important? I need to know. Is my process control in temperature big, or is my raw materials variation big? I have to set that up in the question to allow you to do the right ranking. If your priority is raw materials and they vary all over the place, you're going to choose this one. If your problem is you got a crappy furnace, you're going to choose this one in your ranking. Okay? But the easiest answer is for me to, or the easiest question I could set up for you to answer is which one's going to be the worst. That's unambiguous. Now, if I keep a composition and I tell you that you're going to have 5% impurities of your second phase without specifying it, and you're going to choose the most successful processing procedure, what I'm saying is for these two, you're going to choose a composition here and a composition here because they will be successful. And if it's 5% of impurities, then here are my impurities. So I draw a lever and I take 5%, and then I give you a temperature of 1500. No, sorry, 1420, okay? So I say 5% impurities, 1420. So here's your lever for your impurities. It's going to put you here. 1420 is going to put you here. So there's your composition right there. Right there. Okay. Then for the other one, 5% impurities, which is going to be here. It's going to be a little bit further in. At 1420. Ooh. Is it going to work? Oh, no. So you're screwed. One will work and one won't. And that will come out in the question. Okay, then you say, you realize your mistake. What do you have to do to fix it? And the answer is, go to higher temperature. What temperature? Above 1430. So here's my higher temperature. Here's my higher temperature. Now I can do it. 5% impurity based on the solid here gives me so much liquid and solid, so much liquid and solid. Which one has the lower liquid proportion? C2T or CT2? Which one's got the lower proportion of liquid? It's probably this one, because I drew this pretty close. And that's even further. So you can just sort of mentally draw the lever there, but you'd have to do this with a ruler. Make sure you bring a ruler to the final exam, by the way. Okay, so it's a multi-level question, and that's often what I do, is you have many, many questions on one phase diagram. And so we have so much liquid and so much solid. We've targeted a minimal temperature of 1430 to make this work. And we know how much impurity we're going to have at the end of the day because I fixed it. And then the other thing we might want to look at is if you have temperature fluctuations of plus or minus 9 degrees. I've got to go to 1440 here. Now let's say this is at 1450, okay? If my furnace fluctuates plus or minus 25 degrees, what are the ramifications of this? And the ramifications are, over here, plus or minus 25 degrees is going to take me down to here or up to there, and because it's so steep, the only ramification is the changing viscosity of the liquid. So the solid-liquid ratio stays about the same, and there's no real change of liquid and solid. They stay the same. Okay? But on this one, if I'm plus or minus 25, if I drop below there, it's solidified. And if I go up, you can see there's more of a slope. So the liquid-solid ratio is changing. And this is the kind of question I like to ask because you're contrasting two different situations. One, the solid-liquid ratio doesn't change much, and the phase assemblage doesn't change. And on the other one, it's not the case. They do change. And if you can read it off the diagram, then I know you know what you're doing. You can answer the question. It's really very, very straightforward. But the question may sound a little bit strange because this is, what are the ramifications? Well, do it on the diagram and do what I said and see what it does when it shifts you around in the composition or the temperature or both. All right, so there's quite a bit of information there. If you look at the slopes of the liquid surfaces, the locations of the invariant points, what kind of temperatures you might need to generate a liquid, to do liquid phase densification, or what kind of compositions and temperatures you need to do casting. So there's my next question. If you want to cast CT, is that possible? Can you cast CT? Yeah, it's congruently melting. Could you cast CT2? Well, not under a proper casting process. Of course, you can liquefy it, and you can pick the temperature to liquefy. It's about here. But generally, no, you don't want to cast CT2. And you'll end up with what primary phase? What primary phase are you going to be stuck with in your microstructure? TiO2. Because you need to be able to label these things, and that tells you what's precipitating. Okay? What if I want to cast C2T? Can I do it? What's the minimal temperature I need to do it? 1575. And if I said, what's the minimal temperature to liquefy a composition of CT2, your answer would be whatever that temperature is there. Okay? And remember, CT2, if I am cobalt oxide rich, I have to use a different temperature, and my process control has to be much better. But if I am titanium rich, then I don't need such good process control, and I have a much lower temperature. But of course, I have a different performance temperature too. Okay, so if I give you a composition and a temperature, I say you're going to take a composition and you're going to batch it up, and that composition's right here. It's 87% of something and 13% of the other. What's it 87% of? 87% what? It's close to titanium. Is that weight or mole percent?